And in this case, KEQ is much, much smaller than 1. Okay, now we know that reactants are favored over products. Because to get a small number, we need to have a bigger denominator. Okay, those are the two extreme cases. And then, there are some KEQs. The KEQ is approximately unity, or it is unity. And when it's unity, then essentially reactants are about equal to products. If it's exactly 1, of course they are, but anywhere around unity, of course, these guys are going to be nearly on the order of one another. Say at 0.7 or 0.8, of course, you would have slightly more reactants than products. If it was 1.2 or 1.3, you have more products than reactants, but ever so slightly, okay? These numbers are nearly in balance, okay? So you have a balance of reactants and products. So you can use this knowledge then to understand what's going to happen in a particular chemical reaction if you know its equilibrium constant. And one of the key things, when you think about making your stock solutions in the laboratory, you should think about their solubility, and you should think about solubility equilibria. I want to make sure I leave you enough time for the clicker. Okay, so solubility, a solubility equilibrium example would be like this. If we had copper hydroxide, that's a 2. It looks bad. And we imagine dissolving this in water, so it's a solid. We put it in aqueous solution, and we should yield copper 2 ion and 2 hydroxide ions. Okay. It turns out, though, as exciting as that sounds, is that actually is not very favorable. And it has a very small forward arrow for its solubilization. Okay. And really, if you have copper around hydroxide ions, they would rather come together and make this insoluble solid. Okay. This copper hydroxide. Okay. This is copper 2. Copper 2 ion and hydroxide ion. Copper 2. Yeah, you can put copper 2 hydroxide. Okay. And hydroxide ion. So this would mean, of course, that copper 2 hydroxide is preferred in water. And what would its KEQ be with respect to 1? Much, much less than 1. And if you were to write out, and now, if you were to write out its equilibrium expression, you write out all the aqueous ions, and it turns out that you wouldn't even consider the concentration. You can't really consider the concentration of a solid in an aqueous system. But if you were to write out its equilibrium expression, it would look something like this. But don't worry about this too much yet, because we're gonna worry about this in the future. But you do need to consider the fact that there are 2 hydroxide ions there, and you raise it to the second power. And you don't consider the solid in that equilibrium expression. But we'll worry about that a little bit later, because I know that's going to be a little bit confusing, because we just talked about it being reactants over products over reactants. But in this case, you just ignore the solid because it's not an aqueous entity. All right. So we can consider a few more cases. We can consider copper carbonate, just so everyone is caught up. And this should form copper 2 ions and carbonate ions. It turns out that as I've drawn the arrows here, with a very short arrow in the forward direction, that it's going to have a KEQ, again, much, much lower than 1. Again, copper carbonate is not soluble at all. And but copper sulfate, on the other hand, is highly soluble. So we would show it somehow like this, with the reaction describing its dissolution into copper 2 and sulfate ions is much, much more favorable than the reformation of the solid. And so its KEQ is much, much greater than 1, and copper sulfate is highly soluble. So you can use this technology of differential solubilities to play tricks on ions and quantitatively remove them from solution. I was going to do an example of that. And you can imagine you had aluminum chloride. And aluminum chloride has a KEQ that's much, much greater than 1. It's soluble. Okay? But aluminum hydroxide has a much, much smaller KEQ. It's relatively insoluble. Okay? So you could play games with this knowledge. You could imagine you're in a water treatment plant that wants to get rid of aluminum that's dissolved in water. And in any case, if I put aluminum chloride into this, it would dissolve nicely. Obviously, I'd have more than just 3 chloride ions, but I'm just trying to show us. All 3 of the chloride ions have dissociated from the aluminum 3 ion. And so I basically dissolve this very well at neutral pH, let's say. pH 7, let's say. Now, if we took the solution, though, given this knowledge that I've just given you, and we raise the pH, now, what's going to happen to the hydroxide ion as I raise the pH? Anyone here know? What will happen to the hydroxide ion first? As I raise the pH, I'm going to increase the hydroxide ion concentration. Okay? I'm not. You guys are jumping ahead. I'm going to increase the OH concentration, right? And so in that case, what's going to happen is at the bottom of the vessel, little piles of aluminum hydroxide will appear, and little piles of aluminum hydroxide precipitate, and chloride is left in solution. Okay. So that's what happens. It doesn't matter here how many. All right. So then the other case, of course, is I lower the pH. And when you do that, of course, you increase the proton concentration, of course, when you simultaneously lower the hydroxide concentration. And when you do that, then nothing will happen, right? Because aluminum chloride is perfectly happy, I said, at pH 7. And so everything remains in solution. So everything remains in solution because it was already soluble, and you've yet lowered the hydroxide ion, and protons don't affect the solubility of the aluminum 3 ion, so it stays in solution. So what one could do if one wanted to remove aluminum from water is they could simply just raise the pH and remove the solids. And that's a trick. Now, so we have enough time for the clicker. Yeah. So you can get that out while I'm switching slides. I'm going to skip a slide that I was going to do, which was also going to talk about cleaning up chromium, hexavalent chromium ions from water. But we'll do that next time. And I wanted to talk about something that will be very useful to you for the clicker question. And I've already sort of given you a clue about the Le Chatelier principle. Le Chatelier principle. Should try to use French pronunciation. And the idea, as I said before with my analogy on attentiveness in this classroom. Now, let's say that the major driving force for inattentiveness were, and I don't know if this is true, were cell phones. Okay, I mean, it could be. And that's my hypothesis I'd like to test. So I talked to AT&T, and I told them they're going to shut down the cell tower over Berkeley whenever I wanted to. Okay, yeah, they're down with it. They said that they can tolerate a little loss in revenue for my experiment. And so what I would expect, based on Le Chatelier's principle, is that if I shut down the cell tower, then everyone is going to stop playing with their cell phones, and you guys are going to be bored, so you're going to pay attention to me. And so I'm going to drive the equilibrium towards paying attention to me. And that is Le Chatelier's principle, except for when we do chemical reactions, what we do is we adjust the concentration of reactants or products to drive the reaction one way or the other. Okay? So the other thing that could have happened is AT&T could have said, no, we want to make more money, and we don't care about people paying attention in your classroom. We're going to offer more bandwidth at cheaper prices only during your lecture, Professor Grants. And then, there will only be like 5 people paying attention. So, all right, maybe not, because you guys want to get A's on the exam, which is the other driving force. All right, so anyway, so let's think about acid-base indicators in the same light. Okay, so if we have, and this will illustrate the principle, if I have an indicator, and this is an organic molecule that when it interacts with protons, it will change color. So let's say before it's interacted with this proton, and we'll abbreviate it IND, it's blue. Okay, you have to be a little bit of an artist now, because you have to understand colors. And when it forms a complex, and the indicator becomes protonated, okay, then we have this guy, H-end. And H-end turns out to be yellow. This is what makes it a good indicator. Those two colors, blue and yellow, are easy to distinguish. It didn't go from like blue to, I don't know, turquoise or something like that. It really changed colors, and you can really see a vivid change. And so you can consider then different cases, right? If the indicator has a natural affinity for protons, and that's represented by its natural equilibrium with that proton, we'll later refer to that as a pKa. But let's say we're at the point in which exactly half of the indicator is protonated and half the indicator is unprotonated. At that point in the reaction, remember, then the concentration of H-end over the concentration of end is equal to 1. That's where the KQ at that particular point in the reaction is 1. And what would the color then be if we had an equal mixture of protonated indicator and unprotonated indicator? What color do you guys think it would be? I heard green, because you guys remember the Glad seal Ziploc, right? Yellow and blue makes green. That's why you have to be an artist. Yellow and blue makes green. So yes, the indicator, the overall indicator color is green. Now that, in reality, it's not actually, no molecule by itself is green. It's that there's equal parts blue and equal parts yellow. And when we look at that by eye, we're integrating all those colors together with our eye, and it looks green, okay? So that's one case. But what if we actually, by Le Chatelier's principle, we add H+, i.e. lower the pH? So I basically already taught you this by the aluminum hydroxide example. From this KEQ, if we start out with a KEQ equals 1, and then we add protons, now what color is it going to become? Remember, adding protons will create the HIND species. So it should become yellow. Yeah, so we can even make this thing yellow and blue. And I just want to use colors. Okay. So yes, it becomes yellow. That's why this is great for sensing pH. We just look at it. You just add a little acid, and lo and behold, it turns yellow. So you could tell easily if you added an acid to this indicator. Okay. And now if we instead raise the pH, which means lower the concentration of protons, then what happens? Yeah, it becomes blue. Okay. So that's all you need to know. I mean, there's a lot of other nuances about acid-base indicator chemistry that I'll talk about in detail. But this is the basic principle that the proton becomes a driving force in this reaction. This reaction could go either way. So you guys could either be paying attention to me or not. And instead of changing this, whether you can get to the cell tower or not, or whatever AT&T decides to do to the bandwidth, I'm controlling protons. Okay, and I control protons to change the color. And that's Le Chatelier's principle of changing the direction of the reaction and driving the equilibrium one way or the other. And so the other thing we should put down is that when we add protons and we make it yellow, KEQ is becoming much, much greater than 1, and then KEQ is becoming much, much less than 1. All right, so now we can do the clicker. Even though I maybe could have done the chromium thing, but it'd be too tight. I want to give you a chance. This is hopefully. Oh, I can't show you it yet. Don't cheat. No, I'm just kidding. There's no. Yeah, you guys can talk, of course. I gotta turn this thing on. Clicker. Yeah, so just get your guy fired up and. Okay, people know the answer already. Look at that. Let's see how many people know the answer. 10, 11. You guys are quick. All right, fine. I'll put up the question for the people that really want to see it. So, I've given you an acid-base indicator, and so this is a little tricky. Some people pointed out this is a little tricky, but you should be able to get it. Given the following acid-base indicator, which is red when it's protonated and yellow when it's deprotonated. Remember that red plus yellow, for those of you that don't know your colors, makes orange. And this is equilibrium into H-end. At pH 6, we know that the equilibrium constant of this reaction is unity is 1. What's the color of into pH 6? Okay? And so you have your choices there, A, B, C, D, red, orange, yellow, and colorless. Now, you're going to be stumped about this pH 6 thing, but remember, I gave you all the information you needed. I said at pH 6, equilibrium constant of reaction is unity. So talk amongst yourselves. That's the trick. You'll have to think about that for a minute, but it's a learning exercise, and we can talk about it afterwards. Huh? Oh, sorry. see where we're at. Oh, people are still going strong. We just hit the 400 mark. Okay. It's exciting. We're coming down to the wire. Oh, for people who can't see the bottom choices there. Oh, look, there's choice A way over there. Let's delete that. Still going. All right. Everyone happy with their answer? I'm going to stop it so you can't cheat. Okay. It's not a trick question at all. Okay, so some people, now this is interesting. Many of you got the right answer. It looks like 86% over, about, I don't know, 13, 14%. So, yeah, so many of you got the right answer, which is orange, okay? And I'll explain that here in a second. So you might be confused. You might say, well, Professor Krantz, that's not a pH 7, and that's where you might think that you have equal colors of orange and red. No, that's not true, because I said at pH 6, the equilibrium constant reaction is 1. That essentially means that the pK for this indicator dye is 6. And so then at that point, the reaction is perfectly balanced, and so you'd have orange color at pH 6. If I went to pH 5, what color would it be? No, it would be yellow, because when it's, I'm sorry. No, you're right, you're right, red. When it's protonated at pH 5, it'll turn red, and when you went to higher pHs, like say pH 7 or 8, then it would become yellow, okay? It would never become colorless in this scheme. All right, have a good time in lab, and we'll talk more about equilibrium next time.